Good morning to all. Today, let us start the next lesson, Laws of Motion. In this lecture, I am going to cover the following points: Newton's first law of motion, that is inertia of rest, inertia of motion, and momentum. So, let us start. Aristotle fallacy. Now, Aristotelian law of motion states that an external force is required to keep a body in motion. It was proved wrong by Galileo Galilei and Isaac Newton. Galileo's observation: he took the two slanted boards, and he found that whenever a ball is dropped from one side, it is released it from one plane, then it rolls down and climbs up the other. In the absence of friction, the heights of the ball on both the planes are the same. That is the ideal condition. In practical situation, the height on the second plane is always a little less but never greater. So this was Galileo's observations, that when the ball is dropped from the two plane, then if it is released from the one plane, then it reaches to the other plane, it climbs up to the other plane to the same height in the absence of the friction. Then he showed this experiment. Thus, in case 1, he dropped the ball and he found that the ball is climbed up into the second plane up to the same height. Then he gave in case 2 that the slant of the second plane is little bit decreased. Then to reach up to the same height, the ball has to travel to a longer distance. In the third case, he made the slant of the second plane 0. Then he found that in the absence of the friction, the ball will continue to move. So ball is released from rest in case 1, reaches the same height on the other side in the absence of friction. In case 2, the ball reaches the same height on the other side in the absence of friction but travels longer distance. In case 3, which is limiting case, the ball rolls down and continues to move in the horizontal direction through infinite distance in the absence of friction. So Galileo arrived at a new insight, that the state of rest and the state of uniform linear motion are equivalent. In both the cases, there is no net force acting on the body. So therefore, there is no need to apply an external force to keep a body in uniform motion. So Galileo said, on the basis of these experiments, he found that state of rest and the state of uniform linear motion are equivalent. In absence of any external force, there is no need to apply any external force. In the absence of there is no need to apply an external force to keep the body in uniform motion. We need to apply external force only to encounter the frictional or any other forces, so that the forces sum up to 0 and net external forces. To summarize, if the net external force is 0, a body continues to remain at rest, and a body in uniform motion continues to move with uniform velocity. This was the conclusion made by the Galileo on the basis of its experiments. So that net external force is 0, the body continues to remain at rest, and body in uniform motion then continues to move with uniform motion. This property of the body is called the inertia. Inertia means resistance to change. So Galileo's law of inertia: a body does not change its state of rest or of uniform motion unless an external force compels to change its state. So this was the Galileo's law of inertia, that if unless we won't apply any force, then any body will not change its state. If it is in state of rest, it will continue to be in it. If it is in state of motion, then it will continue to be in it. So on the basis of this, then Newton derived the laws, 3 laws. Today we will discuss the first law. So according to the Newton's first law of motion, every body continues to be in state of rest or of uniform motion in a straight line unless and until compelled by an external force to change its state of rest or of uniform motion. In simple words, if the net external force on a body is zero, its acceleration is zero, or acceleration can be non-zero only if there is a net external force on the body. Now let us see an example that this is a box is kept on a table. Weight is acting in the downward direction because of the force of gravity. The reaction exerted by the table is in the upward direction. Since the block is at rest, the normal reaction R must be equal and opposite to its weight so that the total external force is zero. So now it will continue to be in a state of rest. Now the block remains at rest unless and until it is acted upon by an external force. Let us repeat it again. Now the block is at rest. It is in motion when some external force is applied on it. The ball continues to be in uniform motion unless and until it is acted upon by an external force. The car continues to be in uniform motion in the absence of an external force. Now, inertia. Inertia is the inherent property of the body due to which it resists a change in its state of rest or of uniform motion. Inertia can be understood in parts, that is, inertia of rest, inertia of motion, and inertia of direction. The mass is a measure of the inertia of a body. Heavier objects have more inertia than lighter objects. For example, a stone of size of a football has more inertia than football. Cricket ball has more inertia than a rubber ball of the same size. Inertia of rest. Just look it again. Yes, this is also because of the inertia of rest. When we strike the board moves away, but the coin which is at rest wants to continue to be in the state of rest, so it falls down inside the glass. Similarly, other examples, example of inertia of rest. A passenger in a bus jerks backward when the bus starts suddenly because the passenger tends to be in inertia of rest, whereas the bus is moved away forcefully. When a bedsheet is flicked away suddenly, dust particles falls away as they tends to be in inertia of rest. When a branch of tree carrying a mango is suddenly flicked, mango falls off due to inertia of rest. Now, let us take some examples of inertia of motion. A passenger in a bus jerks forward when the bus stops suddenly because the passenger tends to be in inertia of motion, whereas the bus is stopped forcefully. An athlete, after reaching the finishing point, cannot stop suddenly, or if he stops suddenly, then he falls topping head down. So, for to keep his motion to be zero, he has to run in the same direction for a little while. Car takes some time and moves through some more distance before coming to rest even after the application of the brakes. A rotating fan continues to do so for some time even after the current is switched off. An oscillating simple pendulum bob does not halt at the mean position but continues to move further. When a car or bus turns around a sharp corner, we tend to fall sideways because of our inertia to continue to move in a straight line. It is dangerous to jump out of a moving bus because the jumping man's body is in a state of inertia of motion, but the legs are suddenly stopped by the ground and hence he topples down. So I think inertia in Newton's first law of motion and in law of inertia both are related to each other. On the basis of inertia, the Newton's gave its first law of motion. Now let us discuss the momentum. Momentum is the quantity of motion in a body and it depends on its mass and velocity. Momentum of a body is defined as the product of its mass and velocity. So momentum is equal to mass into velocity, or P is equal to M into V. Momentum is directly proportional to mass. If a cricket ball and a tennis ball move with same velocity, momentum of cricket ball is more because its mass is larger than that of the tennis ball. Momentum is directly proportional to the velocity. If the cricket balls move with different velocity, if two cricket balls move with different velocities, then the momentum of the ball with greater velocity possess more momentum. If a body is at rest, its velocity is zero and hence its momentum is zero. But every moving body possesses momentum. Momentum is a vector quantity. SI unit of momentum is kg meter per second or kg meter minus 1. This is only the way of writing. CGS unit of the momentum is gram centimeter per second or GCM s minus 1, but it is always read as gram centimeter per second or kilogram meter per second. Now, importance of momentum for considering the effect of force on motion. For example, suppose a light vehicle and a heavy vehicle are parked on the horizontal road. A greater force is required to push the truck than the car to bring them to the same speed in same time. Similarly, greater opposing force is required to stop the truck than the car if they are moving with the same speed. So this is on the basis of the momentum. A bullet fired by a gun can easily pierce human tissue before it stops, resulting in casualty. Because here in the bullet fire the speed is very high, so its momentum is very large. The same bullet with moderate speed will not cause much damage. Thus, for a given mass, the greater the speed, the greater is the opposing force needed to stop the body in a certain time. The same force for the same time causes the same change in momentum in different bodies. The force not only depends on the change in momentum, but also on how fast the change is brought. The greater the rate of change of momentum, the greater is the force. The above example do not indicate that momentum is a vector. The following example shows that momentum is a vector. Suppose a stone is whirled with uniform speed in a horizontal circle by means of a string. The magnitude of momentum is constant, but its direction keeps changing continuously. A force is needed to change this momentum vector. This force is provided by hand through the string and it is always felt by the hand. Thank you. That's all for today's.